Hey, everybody, but we're going to look at limits to positive or negative infinity. And again, these are going to be some goofy functions. Starting with this one, I don't even know what to call this function. It's the beginning of the function as a polynomial. It's a cubic, but it's multiplied by an exponential function, e to the minus x. So I'll make an attempt to do this analytically, and then we'll real quick look at the graph, which I have down here, but I'll blow it up in a second. So, real quick, if you just kind of, put in infinity, you get 6 times infinity cubed. You get all this times e to the minus infinity. So, let's take this in 2 parts here. The polynomial part, you get 6 minus 6 times infinity cubed. So, this part is infinite, and 6 minus infinity, means you're going to go towards minus infinity. So that's what happens with the pink part. And I guess let's make the other side green. You're being multiplied by e to the minus infinity. E to a negative big number would go closer to 0, right? E to the infinity would get huge, but negative means reciprocal. So it's really 1 divided by e to an infinite power, which gets close to 0. So the question is, what happens when you have a huge number multiplied by 0? Well, it really depends on how fast to infinity you're going. The bottom line is 0 wins out here. This is going to get closer to 0, and this is going to sound like a lousy explanation, but exponentials work a lot faster than polynomials. When your variable is an exponent, that kind of wins the day. So 0 beats infinity in this case. So you go towards 0. Honestly, the easiest way is to graph this. So I'm going to just kind of blow up this part. I graphed this on Desmos, and you could see pretty quickly here, right? You don't have to plug in 1,000 or 10,000 to see what's going on here. You could see pretty much beyond 10, the y values are getting really close to 0, right? And don't forget, if the horizontal asymptote is at 0, that's what the limit at infinity is. And you could see here, clearly, you don't even need big numbers for this thing to 0 out. So that's why the answer to this one is 0. Just keep in mind, if you could graph a function, you could easily look at it to figure out the limit. But again, let's look at another one here. We'll try to do it analytically first, and then we'll look at the graph to just make sure that we're doing this correctly. Again, this one is somewhat rational, although the numerator is radical. So it's a combination of 2 different types of functions. And whenever we have a fraction, all we look at are the highest power. So if I'm going to rewrite this, it's x approaches infinity of, now the top, you could take the square root of 4 and get 2x, and the bottom you get x cubed. And the bottom has a higher power here, clearly. So when the bottom wins, the fraction goes towards 0. But we could do one more step if we actually wanted to. We could cancel out the x's, and you get the limit of 2 over x squared. So if you plug in infinity, it's a number divided by infinity squared, which is just 2 over a ginormous number, which equals 0, right? But again, if we want to convince ourselves of that, we could take a second and just kind of graph the function. By the way, you see you have a couple vertical asymptotes. What do we care about? We care about at infinity. So at infinity, and again, we don't have to plug in very big numbers. As soon as you get to 10, what's happening? The y values are close to 0. Limits are y values. The limit's 0, right? So it kind of all ties together. And one more quick example here. Again, we have a function that this one is a rational function. There's no radical involved, and all we care about are the highest powers here, right? These matter. Of course, the x to the fifths cancel, and this becomes the limit as x approaches negative infinity of 2/6, which we know is just 1/3. So that's the limit. We just did it analytically, but let's look at the graph just to make sure. And guess what? You don't have to plug in very big X values at all. As soon as you get to 2, you're practically right at 1/3, right here, you know, and I specifically picked my window so you could see it's close to 1/3 here. That's the horizontal asymptote at 1/3 and my limits at 1/3. Remember, limits at infinity are the same as horizontal asymptotes. Okay, hope this helps. Take care.